Okay, now that we've kind of gotten started with this example, we're going to move a little bit further into comparing models or making big changes. And this is part of the steps and so you collect data for each construct right there in letter C, and then you look at exploratory multiple regression analysis of these constructs and consider the possible revisions. And so that's what we're trying to do. But there's kind of two types of changes. There's the bigger ones, the macro changes, and then there's micro changes that are smaller. And we're talking about the big ones this time. So here's our four variables that we talked about last time. And now this is, again, like we already talked about, the fully identified model with all those paths, with every variable is connected to every other variable. Well, and we said that we needed a theory. So we have all these options, these possibilities, but now we got to kind of decide what we think. And so there's tons of possibilities. And so we talked about how this first one right here on the top left has family and need as the exogenous, and then test and dogfight as the y variables. And then we thought maybe that need would be related to dogfighting, but family's just kind of out there related to dogfighting, but not to test scores. And then also, we didn't really like that one because test scores were not related to dogfighting, which we really don't think is the case. I mean, the test is about dogfighting, and so we think it'll be related. So probably won't use that model. Okay, and this other one kind of looks like the model they may be currently using. Basically, where the test is the only thing that they have that's predicting dogfighting skills. But in our model, since we have these other variables, we would suggest, or we might theorize that this model, that family and need might be correlated with, or might have an effect on test scores. But those test scores is what affects dogfighting, or what predicts dogfighting skills, and so that's a pretty strong possibility. So we think that's a pretty good model for us to look at. The next one down here on the right, this one suggests that we're only looking at dogfighting skills, and so this is really basically a multiple regression model, where we are going to predict dogfighting skills from these other three factors. But we kind of feel like these factors might have some other relationships, but this assumes that they're not related. And yeah, that's probably not true. That's one of the advantages of using SEM, or structural equation modeling, is we can model those relationships. And so I'm not sure I like that model either. Now, this fourth one has need and family as predictors, and as they're having an effect on test scores, which then has an effect on dogfighting ability. It also has need and family being correlated, which seems like probably is true, and also suggests that need may have a direct effect on dogfighting. And so this is kind of more the Maverick model, what he might think would be going on, that this intuitive need for speed that a pilot has might have a really strong effect on how good they are at dogfighting. So that's another model that maybe is good. And so basically our two theorists, we have Charlie's model up on the top right, and then Maverick's model on the bottom left. And so we're gonna look and let's compare those and see which one is stronger. And one of the cool things about it is we're not just gonna is we have an empirical method to use to do this. So once you've created the models, and they'll end up kind of looking like this, and they have numbers associated with all these relationships. Just looking at them, you should think of them, they're kind of like regression coefficients, and so that should help it make a little bit more sense. But we're not super concerned with the coefficients right now. We're concerned with the models overall. We are trying to compare the model on the left to the model on the right. Well, the way that we do that is we look at these these two lines down here at the bottom that have red X around them, what's called the fit indices, and so these are just two fit indices of many fit indices that are out there, and usually they have their own advantages. But these are two of the most common. Textbook talks about them, and so we're going to use just these for now. Well, these two. But let's look at both of them and kind of compare them side by side. So when we look at the chi-squared fit indices, it's kind of weird, but in the chi-squared fit index, you want to fail to reject the null. And so when that p-value for the chi-square, if you look at this chi-squared value, so up here on the top with model 1, we have a p-value of 0.03, which is below 0.05, and this chi-square of 6.8. Well, actually, for an SEM or a path analysis model, that's not a good thing. We want our model, our chi-square value, to look like this one down here, where the p-value is above 0.05 and the chi-square is not significant. It's kind of weird, but the goal with the chi-squared fit index is to fail to reject the null. If you reject the null, because what the SEM model does is it's checking the matrix that you made out of your model and comparing it to the default matrix that's in the fully identified model, and trying to see if they explain different amounts of the data. Well, you want them to explain the same amount, which is why you want this chi-squared value to be not significant. You want your model, which has less relationships, to explain the same amount of variance as the fully identified model. And so far, model 2 looks like it's coming out better. Okay, another fit index to look at is the RMSEA, which stands for the root mean square error of approximation. And so with the RMSEA, what you want that value is to be below 0.05. So it's kind of like a p-value. That's not what it is, but I'm not going to go into what it is right now. You can read it, it's in your textbook. Well, looking at these two models, it looks like the root mean square error of approximation is lower in model 2. And this is what we want, since we want the RMSEA to be less than 0.05. So far, it looks like model 2 has better indices of fit to the data. And so that's a really important way, a really good way of empirically comparing two models. So overall, it looks like model 1, the one that they're currently using, doesn't really work as well for the data as model 2 does. And so it looks like model 2 is better. And so we'll move on with that and see if we can find out even better ways to fit this data. But he's going to ask, but what if we need to make smaller changes? How would we evaluate whether just one relationship needs to be included in the model? And this is a good thing to look at, because sometimes your theory is wrong. Sometimes your literature review may reveal that it wasn't quite done right. So we'll move on and talk about smaller changes in the next video.